I'm going to speak today about how would you write controller in Rust, and show some examples with something more known to, I suppose, to the audience, like controller-runtime, compare how it works, internal differences, mostly in spoken form, some lessons learned, some good things, some not so good things, so you can decide if you want to try this for your own personal project or even for something more for the collection. So, yeah, without further ado, you have a link, you have a QR code to follow if you want to see the slides. And let me start. So, I'm going to speak about a library called Kubernetes. It's a CNCF project, which is, I think, already graduated. And it allows you to do many things, like writing controllers in Rust. It's very competitive, let's say, in terms of functionality it provides. It has all the feature richness you would require from writing a controller. And it's built on the Rust ecosystem entirely. You might think about the idea of writing a controller in Rust. It sounds a bit weird because, well, we have Kubernetes ecosystem for some reason. We were using this for multiple years in Golang. There are different libraries like API machinery, client Go, all those things. They are very common to use. They are, let's say, battle tested, etc. And you have lots of things to use and work with. But surprisingly, from my experience, I found that Rust ecosystem within this single framework is capable of replacing many of the functionalities you would require for writing controller. So yeah, as you can see, there's some built-ins like Tokyo, strong type safety. I'm not going to speak much about Rust benefits here, maybe from my personal experience mostly, because they're commonly known, and downsides are also commonly known, but you may decide for yourself. And yeah, controller-runtime is another known library we all use and all pretty much familiar with. It's de facto currently a standard go-to to write a new controller. It's in Golang. You have many examples documented. There's a kubebuilder project which allows you to bootstrap a quick start controller. It has a good documentation again, and anything upstream is currently built on this project. So it's good, but that's why I decided to compare those things to see how it is similar to controller runtime and show you what you can do with this. So first of all, if we start with a quick start, there's going to be lots of examples. I'm going to just speak through this. If you don't know Rust or you don't have familiarity with this, don't get scared. This is a simple main method which already opens a client connection to your Kubernetes cluster. That's all you need. It uses default kubeconfig. As you can see from the difference on the definition, it doesn't use a client as in controller runtime, which typically works on the interface of object and basically mutates the structure you pass to it. It actually defines an API type. It's similar in comparison. There are a couple of things different. For example, well, you have to separate those pods examples. It's a namespace object from class scoped objects like namespace, for example. So there are some other things, but here Rust actually provides you lots of type constraints you can use and rely upon. But everything else besides that, like client, get, list, update, create, methods, patches, all available from API, fully stable, and it's all async. As you can see, it uses Tokyo. So you just create essentially a simple main program because you do some things, some simple CLI stuff. I'm going to show an example later how CLI works in this scenario, and it's done. And there are many things already, as you can see in this simple example, which are different. Like there's no if, error, else statements like in Golang, but there is error handling with question marks. There's also everything in asynchronous fashion, so if you start multiple threads of the same main program or something more complex, it will not hang over itself. And yeah, that's still the same thing. And if you go to the next slide, that's the same thing written in controller runtime. Very similar. We also use core types, define upstream. But you may notice that in previous slide, there is a difference. There is a Kubernetes Open API. That's one of the crates it all relies upon. It's a very simple project, which was written by some person upstream, and they typically just, for each Kubernetes release, synchronize definitions of Open API types exposed by Kubernetes to create a fully fledged set of core resources for you to use. So you have everything there is upstream already. We'll come to custom resources later, but you can do this as well. And yeah, same thing, just list. It's essentially equivalent. As you can see, I here omitted the error handling because it already won't fit on the slide, because, well, it's easy to understand what's going on, but previous is more complex and more dense. So that's a smidge of those things. And, well, default client creation, you have all options to derive your config, whether it's running from the cluster itself, or it's running from some local environment, or you pass the kubeconfig as a variable. All typical expectations of how you build your connectivity with the cluster still persist in this scenario, because it still implements all the constraints, constants, and all the contracts API server provides. API, yeah, it's different, but it takes some using to. And trait extensions. As you may know, in Rust there is not interfaces but traits, and those are pretty powerful in some scenarios, especially if you want to do something like default implementations for traits, or build some sort of functionality and extend upon those traits. You can do lots of interesting things. Maybe provide an example if I have some time in the later slides, but that's what you can expect, and that's all built in for a language, so you don't have to build your own enormous base of code to write something pretty simple, which basically exists in your head because you have lots of type system things to rely upon. And, well, controller-runtime is also simple. We have lots of core resources. We typically, for these resources, we provide the pod list. All those things are already exposed to the normal API from the API machinery, from upstream definitions. You can use client Go if you want to do the same thing. So controller-runtime is pretty beautiful in this regard. So you don't have to choose in this area. But in comparison, I would say that, yeah, if you want to do some operations with client Go, you have to write many things on your own. But generally speaking, for some very simple, like GET request, it's less boilerplate. You don't have to expect those things to be written for you on your own. But let's see, what's else? We have difference here. There is a difference, which I showed in the first slide, is error handling. In Golang, it's easy. Error handling, just return those things. For Rust, there are a couple of things you can work around this issue, or make it even beautiful and more easy to use. As you can see, for example, in this case, I'm doing some sort of namespace selection and fetching a config map from some location. And I use the namespace as a source for this config map. As you may expect, if this operation fails, we have to return some error message. And we can define those error messages not in the code where you write this thing. So basically what you get from this example is a happy path. You can follow it without even thinking about this. But if you want a strict type-safe definition of errors, you can use this error. It allows you to derive enums with lots of definitions of how to handle those errors. So for example, here, by default, in this case, this client get returns a kube error. And this is what I expect with the result. And if this fails, I don't have to handle this anymore. I will get the log message if I have a login enabled. And everything contextual can be defined in a structure you want to preserve in this scenario. You can format those things. It's very powerful. But also a bit more complex than you might want for a simple example application as in Golang. But that's an example of those things. What you can do simpler, anyhow. And what I used in, I guess, CLI tool, talk about this later, it becomes as if you write in Golang. You just question mark anything. You can define some additional context. I don't have this information here, I think. But you can write some additional context for the error message. But typically, you just focus on the heavy part, and you know these operations has to happen all sequentially. There's just pseudocode in here. And one interesting thing, so a couple of details. As you can see, Rust leans heavily into declarative macros on top of each method. So, for example, with tracing, you can define this stuff. What it says, it basically says to you that you want to expose the node name. It comes from the interface, from the trait on the node object, and you want to expose your error. So if the error happens on any line of this code, it will be shown in the logs. You will have the context and information to debug those things later. But otherwise, this code is self-contained, very easy to read, I would say. Well, does nothing, but as an example, I would say it serves its purpose. And the question mark is the error handling. If error not equals nil, return this error. That's equivalent, so you don't have those still statistic choices. You can choose how to do this. I mean, when we speak about Rust, we think about probably has type safety, it has some performance benefits. For my personal experience, I would say they are still there, even though in comparison with Golang, they are both system programming languages. We still work with essential structures in JSON. We serialize, deserialize, move things around, send some external API requests, report something in the status, and do it with it. It's the same reconcile method, it's the same logic as in controller-runtime, but you still gain some of benefits of Rust ecosystem in terms of amount of memory. I would say in the controller we observed like 10-fold less usage of memory for the same essentially code. Performance, I have a funny story to tell. It's actually related to some controller I wrote. I was trying to debug this stuff. I was trying to make it like go broke. I just started this on my machine. It was running. I was like, okay, I have a couple of resources I apply. Now I need to remove one of those. What if it doesn't catch the error, doesn't catch the event, doesn't catch the recreate this resource? I remove it, nothing happens. I'm using KNS, by the way, so it's just a visualization of those things. There is no difference. I tried it a couple of times thinking maybe there's a finalizer. I don't set anything. Nothing should be happening. But then I noticed that creation time stuff is always different. It was so fast that it didn't pick up this event at all. So well, it worked. It's a good thing. It was so weird to see those things because you never see this in any implementation of Golang. Because of one of the differences I'll come to later, it's a cache usage. So this client in Kubernetes typically is non-cached. So you send requests directly to the server. But with server-side caching, implementing upstream, and all those things, that might not be an issue for you. But, well, yeah, this is an important thing. And I think for my purposes, I don't think that it's very important to keep the cleanest, best ideal scenarios for us when you try to basically convert within those two ecosystems. So cloning stuff is okay until it works for you, and performance can be optimized later. Simplicity is also important here because, well, otherwise some things in Rust take time to write, and keeping it simple sometimes helps you to work with compiler much better than otherwise you have to in Golang. Yeah? And I'm showing Tokyo a couple of times. Basically, when you see Kubernetes and see those examples, most of it is just framework for development used for many other projects besides this Kubernetes. So this means that you can rely upon stability of those features and that this stuff is beta tested as well, and it's used in production for many people, which is not the same thing for Kubernetes. You don't use Kubernetes libraries otherwise from outside of Kubernetes ecosystem, I think. Well, maybe there's a benefit. And controller-runtime, we all know this. We all work with this. It's well optimized. You can do lots of tinkering. You can do lots of configuration options for your controller, for your managers. You can do, well, if you know what you're doing, you can write anything I'm showing here, and even beyond, but that requires a lot of investment of time. And it's going way further from the quick start guides they present in many occasions, which is a bit different, I would say. One thing I noticed with Kubernetes, you don't have to care about QStack as much. It's always the same pattern, and you can extend upon those definitions because there are extension points. You don't have to put anything upstream. Any, let's say, injection for the client code can be done through Tower framework, which is based upon, in this scenario. There's the layers. You can process requests. You can do some additional operations. You can do some anti-patterns in this scenario, like working with what you store in cache. If you need it, but for cache, I guess, optimization, that could work, for example. Not that I'm recommending this, but speaking just simplicity of this allows you to do many things. Yeah, for caching, now as we're speaking about this, there is a couple of things. So as I said, client is not cached, but all controller-related stuff, when you open a watch for the API server to see some events from some resource, or you have to reconcile other things based on some ownership label or references or some other specific mapping logic, that's all can be implemented in Kubernetes, and it uses the cached implementation under the hood, because you have to know what you already have established in your controller. And it's still the same thing. One of the interesting ideas behind this implementation, it uses streams. Streams are extensible. You can do some fine-grained control. You essentially get this builder pattern we typically use to in good practices to do things upon this. It takes a bit of tinkering to get it right because of the type system, but then you gain lots of pleasant experiences and simplifications and reduction in the code without reduction of clarity and what happens under the hood. Those are pluses. I would say, otherwise, coming to controller runtime, one of the minuses and one of the pluses of controller runtime is what it does with typical client stuff. When you open a request to, some sort of client list for pods, it typically starts with creating a cache which is regulated. It's open, like the content of the pods, for example, you listed, will always come from the cache from this point forward. And that's useful, but you have to know what you're doing, and you know that probably this thing couldn't be optimized less if you add some additional code, which does something else. So it has to account for those things, even though it's very occasional. And also client Go. It's been written from the beginning. It's used in Kubernetes core everywhere. And shared informers is the source for this population of the caches. So it's established pattern. We don't have to think about this. I think it's a big plus for controller runtime. But then, as I said before, if you write, and I'll show this in examples, some additional code, it becomes very complex pretty quickly. So coming to controller setup, I'll start with controller runtime. Very usual stuff. We start with reconcile. We define some sort of ownership model on the resource. And we just start with the manager. Very simple. Each reconcile does something. Here it does nothing, but that's the point of this code. Kubernetes, same thing, almost. So it also uses reconcile. It also returns the result. Requeue, you can define some requeue, for example, to get a result. You can define some error handling as well. No, it's just unfortunate. As you can see, ownership as well. So I opened some APIs for different resources, for pods, custom resources. And here we come into the definitions of Kubernetes, what it allows you to do. Right, custom resources you want to use. And you do the reconcile. That's the same thing. So nothing much to it. But we can do some unstructured resources work, which is a bit weird in controller runtime. That's how you do something which you don't rely upon as API overall, and you don't care about content, or it can change. You don't want to have this schema. Here, Kubernetes is actually much better. This is the same thing written in the previous slide. You don't have to define those things. You can rely upon definitions of pod. It's a core, GVK, resource, kind pod, type, v1. And this thing is already derived from the source of this object, from the type. So you can declare a unstructured object, which is called dynamic object in this scenario, and work as usual with this. There's no difference beyond this point. As you prefer, you can look through the documentation for some examples if you want to. But now we come to custom resources. We typically define something simple we want to work with. If we don't want to work with config maps or other things because of anti-patterns, and it's de facto the standard way of defining some sort of declarative logic for your eventual consistency pattern. And this is controller-runtime. Kubebuilder provides you by default those things. But what we found from the experience, if you write it for the first time, it's beautiful. You have customized, you have all those CRDs, you have all the bug generated for you. You can expand upon those things. It's beautiful unless you start adding some custom stuff. And if you forget running this kubebuilder init once again and you derive from this pattern, you are out in the wild. You have to write all those things on your own. All those kubebuilder annotations you have in this scenario, they are actually has to be written by hand. So there is a lot of error proneness to this. There's, without reading documentation first, with lots of places where it can appear, what it means, you won't get what it does under the hood. And you may forget something. No one will take you with your hand and lead you to some correct solution. So here, though, this is how you define a custom resource in Kubernetes. It's a bit complex. It's, again, microservices. As you can see here, one of them is custom resource. But you get all those things, and if it compiles, which it will, you can reliably say that everything under the hood of this is a custom resource you can just create. Yeah, forget about this. You don't have to think about that. Lots of things in derive are just magic. In Golang, we typically have, for example, deep copy definitions we have to write and maintain a separate file. You can go through this, same thing as here. You can go through expanded macroses to see what it generates. We don't have to, because compiler will take care of any errors for you, expose all those things, and you don't see them, unless you're doing something custom. And it's very hard to make it go broken. Yeah, so it's very easy. And we come into some anti-patterns, but what I found in some controller examples, when you integrate with existing ecosystem, which is, by the way, the point of Rust is not to replace those things, but to work together with what we already established. Sometimes we have some legacy code, and we have to work with config maps from time to time. We can do structured config maps in this scenario. What you see here is an example of CRD. I think I forgot to derive CRD in this scenario, but for the sake of completeness, this CRD name is another serialized stance in the derive. And what it does is that you expect a config map to have the certificate field, or the secret to have the certificate field. And you can just essentially open an API on this type and get a resource. If you get the resource and returns an object, ready to complete. You have all the serialized stuff in it. You don't have to write this code on your own. You don't have to worry about this. Even some complex stuff, for example, when you return a config map, it's a JSON, it has some YAML configuration inside of this. CRD will take care of this serialization patterns for you. And it becomes so clean to work with this, in my opinion, that we don't want to go back from that. So then coming to some other things you can do. Here's an example of what we did in an operator fleet. It's an operator for cluster API ecosystem. And since it's written in Golang, the only extension point we have to rely upon is the customer resources they expose. And for that, there is a project, simple one, cluster API RS. What it does, it simply uses a copium, another CLI tool, exposed by Kubernetes within the ecosystem, to generate Rust definitions from this CRD structure. You can use anything, take any source of CRD you have currently in Golang, try it out, it will most certainly work. Cluster API is quite complex. I never saw any issues with this generation. And you get the resource. But then there's a new type pattern in Rust and those things. I still want to write my own type and work with this type to extend components and add some methods to this cluster type. So what I'm doing here, I'm just inheriting this resource. what it does under the hood, it already treats this, it generates all the implementations for the traits. It becomes an object you can fetch upon. As you can see, API already works with this. You have all the specs, statuses, and all those things are coming from upstream, always synchronized. The bot can update your new versions. You don't have to worry about this anymore. And new release is just a new bump of API version, and it's done. So kind of simple. And don't forget, nothing of this kind is a magic. It's all compile validated. So if any error occurs, you can debug it. You know that something is broken. Otherwise, it's not. But I mean, in some cases, I already came up to some limitations of this, but it's similar with Golang. If you have situations when you have a couple of versions of controller-runtime imported in different places, you have to get rid of this dependency. You have to separate those things so you can define your own versioning in some examples. So unfortunately, this example has some downside of being, well, it returns lots of errors if the Kubernetes upstream, for example, cluster API errors, version is different with what you have in your code. Probably not Kubernetes, but Kubernetes Open API in this scenario. But you can still work around those things. This is still exposes all the code which is written under the hood. But it's like lesson learned. Something which looks good doesn't always have to be production ready, but you can still try it. If you control all those definitions on your own, that's one way to do this. And then CRD validation. We have lots of very complex stuff for cell expression language in controller-runtime, messages, etc. It's all very useful, especially if you don't want to use webhooks, if you don't want to care about certificates. It comes with lots of simplifications. But as you can see, it's a bit hard to read, hard to maintain. Again, nothing from this. If I forget to write a rule or something, you'll probably just not even fail, but just forget to add this rule entirely. For Rust, we have extension, which is called kubeschema. So the custom resource integrates with kubeschema. And on its own, what it provides, validation keyword. Same thing, you just write a string, and that's what's going to be displayed in your CRD. And you can say, for example, that the name of this resource, always singleton. If you want to have a structure, it has to be non-empty with a field. So, and nothing from this will compile unless it's already correct. So that's also great. And this Xcube extension, these derived standards, also have some server-side apply logic you want to define. Sometimes you have several managers to work on some custom resource, and those apply, I would say, patches to the same field of strings. You can define some NOR strategies, same thing as in Golang. It's a very, I guess, complex feature, but it's still there. So from this point forward, there's no gap, right? Some other, I guess, honorable mentions. What I used in the project and found very useful is a club CLI. So what I wrote, it's called CrustGather. What it does, it collects resources from your cluster, from everywhere across the cluster, any customers of anything, all the pod logs, and stores in the file system. And when I started this, I was like, why would I do this? I'm a lazy developer. I don't want to write lots of code. It feels like a bit too much to me. But Club showed me that some things can be done very simply. When I'm writing this short stance, as you can see here, there's an argument, so it parses. There's some long, short definition, so it could be used as S. You can do some action append. That means you can have multiple secrets, and they're going to be all stored in this secrets string. This documentation results in documentation in the code. So you have all this information down below. Examples, etc. It's already could be used in the CLI as is. But then set the default and set the allowed me to also use this information as a structured format. So I can provide a config with these secrets prepared. So this one line of code, essentially all this information served me three purposes. I wanted to write documentation. It was ready to be used in CLI, and it was ready to use to be as a config map, to use. So I found this very interesting to work with, and there is no comparison in Golang from my side. And what it does, the cast gather, it's a very simple thing. So we just basically create a cluster. No, I'll just keep further along. It's a kubectl plugin, so we can install crew, and with crew install kubectl cast gather. Something starts up, K9s works as usual, and now we just, kubectl cast gather collect. And once it happens, lots of logs, some errors, everything is parallelized, everything tries to be graceful with the API server to retrieve things in exponential backoff scenario. But once it finishes, you have everything you need. You can go through file system and look through things. You can delete the cluster. But now, one important thing, you don't have to even worry about this, because CastGather implements an API server, similar replica, which serves your file system as if it was a real cluster. So I just start the serve command, and there's a kubeconfig for this, and it's usual. We can debug all those logs, see all those things, what happened before the failure, why the test failed. You can store artifacts in GitHub Actions, and it's very useful. It was so much helpful for some flakes, especially when you integrate with some external systems you don't know about details. Yeah, it's seamless. So nothing of this would be possible without Rust type-strip pattern, I would say, because it was all written as enums converted to another enums to another enums. And this way, this whole thing was going from the source of truth. I know that the API server is fully guaranteed in terms of what it provides, and file system locations I defined are also correct. So I can basically transfer this truth from one source to another, and then I can serve those things from API server standpoint without many additional interactions. And I can actually have another demo, but it's like for other purposes. We can record and replay, so we can start this serving, this collection from some point, wait for some time, and see the changes in the resources, and then replay this whole thing from the beginning to the end. It's more of a fun project. I don't think there's any use, but it's also possible because, well, the structure of this with Rust allows to do those things without much thinking. Okay. And current replay, this is the demo, and the controller. So that's a real example of controller running in the cluster. Just a fleet GitOps integration, which allows you to basically make for cluster API fleet instance and use a Git source to apply your manifests, your Helm charts, your anything in the cluster, all written in Rust. I mean, the demo is pretty long, but if you want to watch, it's all in the demo. So that was written in Rust. You can see the custom resource here, the freedom config. Anything defined here is essentially written in what I showed. There's no additional logic. It's a bit outdated as well, but it serves the purpose. And yeah. Anyway, let's not go into details, but it's more of an example of what you can do. So, and for the copium itself, I mentioned this a couple of times, but the source of Golang definitions you have exposed as CRD format. You can just install copium, and that's the command you have to run to generate the content of CRD. And you can try it on your own to transfer this project to something different, and try those things I showed you by yourself if you wish to. There are also some examples upstream, like Gateway API, Rust bindings, and lots of other things, like Cluster API RS and Fleet API RS. They all automatically synced on each release with this CLI tool. So it's very useful. Though one of the gaps I observed, and maybe it's still a problem, is testing. Controller-runtime exposes end test. End test is very useful. You can essentially start a set of etcd API cell replica and do your actual cluster interaction and start a controller on it. It will behave as usual. There is nothing as such for Rust, but you have Quark. So again, integrating with the existing ecosystem, just start a Quark cluster and work with this, or start a current cluster and work with this. Just kindly keep still, wait for it. Yeah, just file, one of those things you can use. It's a similar to makefile, and keep still, wait is actually great. We just define conditions, what we expect to see at some point, timeouts, etc. It's very simple, but it makes the job done. Okay, so what's missing?
We have overtime.
Yeah, I think if you want to look into this, there are more of conclusion. And if any questions, feel free to ask. Thank you very much.